Okay, right. So today I would like to give you two problems that they're all from previous comprehensive exam. And I think it's good for you guys to see these problems, like see the level of difficulties and also it's also related to what you learned in class. So from next week, we will start the perturbation discussion. So if you have any suggestion about the problems or any topics you want me to go through, just let me know. Right. So let's let's look at the first problem, and I may give you several minutes to think about it. Then we can go through together. Okay. Also, let me know if you think the problem is unclear. I can clarify.
Just to clarify, did the specified eigenvalues, or is that only for M1 or is that MI?
M1.
Okay.
Yeah. So do you guys want me to go through this problem now, or you need more time to think about it? Or maybe you can just go through it slowly.
Well, I tried one thing and it didn't work, so I have no other ideas.
It's okay, yeah. Yeah, we can go through it slowly, step by step. Yeah. Okay, so
I have a question, first of all. It's a linear algebra thing. So if we know that M1 is diagonalizable in its eigenbasis with those eigenvalues along the diagonal, can we infer the same thing about M2 and M3 necessarily, or is that not valid just from the commutator?
not valid, just like what you said, because they are not commute, so.
Okay, I see, Yeah, good.
Yeah, just like, yeah. Basically here you can regard this kind of MI as L, like the spin or the spin algebra, whatever, right? They're by the same algebra. They're both SU2 in algebra.
But couldn't they still be diagonalizable in a different eigenbasis?
Of course, yeah.
Yeah. So I'm just wondering whether we're allowed to assume that they're all diagonalizable in its different eigenbases, not simultaneously.
Yeah, they're all diagonalizable, right? Right. Because they're Hermitian, right? Hermitian matrices are always diagonalizable because they stand for some measurable quantities, and that's it. Also, the diagonal elements are always real. Okay, so this problem tells us the eigenvalue of M1. We can think of M1 as SD has following eigenvalues. So first is plus minus 2. The degeneracy is 1. And also it has eigenvalue plus minus 3/2 with degeneracy 8. And also plus minus 1 with degeneracy 28. And so on and so forth. I just copy this. So now we want to see what's the eigenvalue for this total S square, right? Okay, so because we have M equal to plus minus 1, meaning that there must be a spin 2 representation, right? Because if one spin 2 would give us M equal to plus minus 2, and M equal to plus minus 1, and M equal to 0. And when from the condition, we know there's a 1 m equal to plus or minus 2, meaning that there's only one spin 2. So this tells us the okay, so m squared is a very big matrix, which is times, and there may be different blocks, and each blocks corresponding to a spin representation. So there must be one and only one spin 2 representation. And this would give us 1 m equal to plus minus 2, right? Okay, so let's look at this guy. Now we know there in total there are 28 plus minus 2, but there are already 1 from the spin 1, meaning that there must be 27 spin 1 representation, which would give us plus 1 and also m equals 0. So there are 27. So there's a 1 m equal to plus minus 1 from spin 2 representation, and also 27 plus minus 1 from the spin 1 representation. In total, it would give us 28 plus minus 1. And you can do similar analysis for this spin 0. So spin 0 only give us m equals 0, right? And to have this 70 m0, m equals 0 in total, we would need how many? 70 minus 1. This one is from the spin 2 representation, and also 27 from the spin 1 representation, which would give us how many? 42. Yeah, 42. Any questions about what I'm saying here?
I mean, this is very SU2, like this is very SU2 dependent. Is this just sort of? I mean, I guess I'll just ask, like, is this just like a fun comp problem that is meant to get us to recognize SU2 stuff, or does this have broader implications in physics?
I don't think so. All this analysis depends on this commutator. This is SU2 in the algebra.
Okay, yeah, that makes sense.
Yeah, it helps you somehow to understand this kind of different spins, the direct sum of these different representations, stuff like that, I guess. It's a quite fun comprehensive exam problem. Right, and similarly, you can, because there are 8, there are 8 3/2, meaning that there are 8 spin 3/2 representation, because this would give us m equal to plus minus 3/2. The 8 degeneracy is 8, and also m equal to plus minus 1. It's also 8. Also, we know there are 56 plus minus 1/2, meaning that there must be 56 minus 8, which is 48, I think. 48 spin 1/2 representation. So you can say, okay, so let's add another page. So you can say, okay, let's summarize what we have so far. We have one spin 2 and 27 spin 1. How many spin 0? 42 spin 0. And also 8 spin 3/2 and 48 spin 1/2. Of course, you know this the eigenvalue course for the spin 1/2. So spin 2 is let's see, it's 2 times 3, which is 6, and it's 1 times 2, which is 2, and this guy is 0, and this guy is times, which is this is times 1, something like that. The degeneracy is given by 2s plus 1, right? We just plug in. This guy is 5. This is 3, and sorry, this is for one spin 2, but there's only one spin 2 times 1 is 5, but there 27 spin 1, so times 27. Similarly, the degeneracy for spin 0 is 1, but there are 42 spin 0. And this guy is how many? Times 2 plus 1, which is 4, times 8. And this is 2 times 48. Get a number 5. And yeah, so here you get a number, get a number, get a number. If you add them together, you would get the total dimension of your Hilbert space, of your dimension of your matrix, which is this number. Yeah, basically this is how we solve this problem. Yeah. Any question about this one? Yeah, I would say it's a quite fun problem. Yeah. Not once you understand what's going on here, there really not much calculation you need to do. You just need to do the counting. Okay, so let's look at the next problem. It's also about symmetry, translation, whatever. Yeah, you may take a look and think about it. How would you approach this problem if you have this problem in your exam? Or so just let me know if you find anything unclear. Yeah, maybe we can go through the part A and part B first, and then give you some time to think about part C, D, E. Yeah. It's a quite known problem. I guess the final goal is to calculate the eigenvalue of this Hamiltonian H. And to help you to calculate the eigenvalues, it breaks down into this kind of several steps to guide you through this. Okay, so let's look at part A. Okay, so first let's get some intuition about this problem. What's going on here? So basically, the system has two n sides. So first side, second side, face. Something like this. And by the way, the reason why I draw one is bigger, one is smaller is because you can say when n equal to odd number, so this nh n equal to minus h a naught, and n equal to even number, this guy is a naught. So you can this implies the even sides and the odd sides somehow different, right? Okay, so oops. The first part just wants us to show, by the way, there are two operators, k. K just tells you whether the side you're looking at is even or odd, right? That's basically what the operator k means. And the t is just a translation operator. It's translated by one lattice side, by one lattice distance. Okay, so first we need to prove operator k and t, they are anti-commute. So kt equal to 0. To show that, we just need to show k and t plus t and k acting on any state in the Hilbert space is 0. Then this guy is 0, right? This is how we prove operator identities. To prove this is true, we only need to prove kt plus tk acting on any basis in the Hilbert space. If this guy equal to 0, then of course for any n, then it's true. Then this guy is true. So to show that, it's quite straightforward. So t acting on n give us n plus 1. K acting on n is just like this, according to the definition here. And this k acting on this guy would give us minus 1 to n plus 1. And this guy acting on n is n plus 1. So this is, you can say this is 0, right? So the anti-commute. Any question about this part? Okay, so I guess it's very straightforward. For the we also need to show the k commute with t square. Physically, this is very obvious, right? Because if you translate the lattice by two lattice constant, it will not change the parity of the side, right? 1 translated to 7, sorry, 1 translated to 3, 3 translated to 5. They're all odd size. And the 2 translated to 4, 4 translated to 6, and yeah. The parity is preserved. So Okay, so to verify this is true, you can use the same trick. You just need to prove this guy equal to kt squared equal to t squared k, and act them on n. So this is the left hand side, which is k t squared. T squared just give us this. So this is minus n plus 2. Right hand side is t squared k, which, oops, this k acting on this guy is minus n, and t squared acting on this guy is n plus 2. So they're equal, right? So this is true. Any question about this part? Okay, so it's quite straightforward. We solve part A. So for part B, I would say the most straightforward way to do the part B is to write down the expression for the Hamiltonian in the matrix form, right? So the problem tells us, by the way, this system is 2n by 2n, right? From this guy, we know the diagonal elements is minus a naught, minus a naught, keep going on, right? So the basis is 1, 2, 3, 4, something like that. And the off diagonal elements is given by this, which is a1, keep going on. Here's also a1, like this. So this is a Hamiltonian. Now let's say what is the k in matrix form. K is also 2m, oops, 2m by 2m matrix, right? Okay, let's oops. Okay, yeah, nice. Let's write our k here. Okay, let's write a k here. K, you can say k is also diagonal in this 1, 2, 3, 4 bases. The diagonal elements is given by minus 1, 1, minus 1, 1, minus 1, stuff like that. And t is not Hermitian, equals t n equal to m plus 1. And the only non-zero element is given by this, which is 1. So this element is, for example, n equal to 1, this would be t21, which is this guy. So everywhere is 0 except this, right? Any question about this part, the matrix form of h, k, and t? Okay, so once you have this, it's straightforward to write down the h in terms of k and t. H equal to a naught times k. This term would give us the diagonal elements of h, and plus a1t. This would give us this off diagonal element. So this is this one, this a1, and also plus a1t dagger would give us this a1. So this is the expression. So any question?
I have a tangential question. Is this the sort of stuff that you would actually use in like solid state? This sort of operators?
Yeah, actually, yeah, you're right. But nowadays, people usually use the second quantization notation, not using this kind of cat bra. But yeah, you're right. So you're totally correct. If we write, let's write in another way, h and and h and right. This is Hamiltonian, and I'm just trying to give you some intuition and connect, make some connections to the solid state Hamiltonian we usually use. Okay, so we only need to evaluate this guy. This is a number, right? So it's like this. This number is non-zero only when your m equal to n, or m equal to m plus 1, or m equal to m minus 1. So there's three terms. When m equal to n, so it's replaced by n. This is given by this a naught minus n, and if m equal to n plus 1, this would give us a 1. So it's a 1, and m is m plus 1. And this is also a so basically the Hamiltonian is given by n a naught n plus n a 1 n plus 1 plus n a 1 n plus 1. The third term is just the Hermitian conjugate of the second term to make the total Hamiltonian to be Hermitian, right? And the physical meaning is also clear. So the first term describes the on-site potential. Basically, I have some size, and this A naught tells us how much energy I need to pay to put a particle on some site. And this A1 tells us the probability for the particle to hop from one side to another side, to the nearest neighbor site. And in the second quantization notation, it's nothing but this kind of if it's a fermion, we usually use Cn plus A1 and Cn dagger Cn plus 1 plus the Hermitian conjugates. So this is a Hamiltonian you usually say in solid state or in condensed matter physics. And the spectrum or it's also clear, usually something like this. And as you will say, the spectrum or the eigenvalue for this Hamiltonian also looks something like this. And this, yeah. Okay, so I think we have 10 minutes left. I will just keep going. Feel free to stop me if you get confused somewhere. Yeah, thanks for asking. Okay. So let me also try to. Okay, so the part C, we need to find the eigenvalue, sorry, eigencats for both k and t squared, because they commute with each other, meaning that we can diagonalize them at the same time, right? So to do that, you first need to notice that k acting on any even size 1, 3, 4, up to 2n minus 1 would give us minus 1, 3, something like that, right? And k acting on odd size, sorry, this is odd, this is even. 6 to n would give us plus sign. This. So now, of course, we know t acting on 1 or any set k, set n, it will give us n plus 1, meaning that this cat n is not the eigencat of the t operator, of course, also t square operator. So to find the t square, the eigencat for t square, we would like to assume generally okay, let's assume cat psi is the eigencat for t square. Then this guy can be written in this form. Right? Or let's use another coefficients. Sorry. The reason why I use the all even size, also all odd size or all even size, is because we want to make sure this guy or this guy are still the eigencat for operator k. So basically, we only can do some linear superposition within this subspace or within this subspace. If we add another even side to this cat, for example 4, then this cat psi no longer the eigencat of my operator k, right? So this is the reason why I chose them to be this linear superposition or this superposition. Let's label this as minus psi. This label as plus psi. This minus or plus corresponding to the eigenstate for eigenvalue for k. K acting on this guy would give us a minus sign. K acting on this plus psi would give us a plus sign. Now to make sure t squared acting on this guy give us this, you just need to write down the left-hand side and the right-hand side and make them equal. You get a condition and you solve it. That's it. So let's do it for the minus side and to see what will happen. So the left-hand side would give us, it's quite some tedious calculation, but it's okay. It's much better than your last homework, right? Okay, this guy translate by 2, so 1 becomes 3, and 3 becomes 4, and 5 becomes 7. And this guy, because the boundary condition, according to the problem, it becomes 1, right? 2m plus, or plus 1, and this 1. So I just, okay, so, oops. I just move this term to the front. I just want to order the cats according to the number. Like this. And this is the left-hand side. Right-hand side is lambda times A1 plus this, which is lambda A1, 1 plus lambda A2, 3 plus this. So if we want this guy to be true, meaning that the coefficients must be the same. So we get a set of equations. An equal to lambda A1, and A1 equal to lambda A2, and A2 equal to lambda A3, and dot dot AM minus 1 equal to lambda AN. Is it clear? Okay, so just to make sure you understand what I'm saying, what I'm doing here is nothing but trying to plot to get the equations, a set of equations from this equation. And we know we assume the minus side in this form is in this form, and we can calculate the left-hand side, we can calculate the right-hand side, and compare the coefficients of each term, we get a set of equations. And lambda is the eigenvalue we assumed for this t square. Yeah. So you notice that if you this would implies lambda to nth power equal to 1, because if you times all the terms together, all the equations together, the right-hand side would give us, the left-hand side would give us an, a1, a2, an minus 1. The right-hand side would give us lambda to the nth power, and a1, a2, an. And this cancel out, left with lambda n equal to 1.
But I think the same thing would happen if you would add them all together, right?
If you add them together, okay, that's correct. Yeah. Wait. If you add them together,
then you'll get that lambda is equal to 1.
Okay, if you add them together, the lambda 1. Okay, that's really a tricky question, I see. So lambda 1 plus lambda 2 plus up to lambda n. It turns out this guy to be 0. This guy is 0. Because eventually you will say this lambda 1 is some exponential I theta, this guy is exponential 2 theta, exponential n theta. So it's kind of a, if you add them together, eventually they all cancel out and give us 0. but this does not apply to our situation, our calculation here. This A1 times AN equal to lambda times A1 times AN. You would say, okay, maybe there's some value AI is 0, and other where A are not, so other AIs are non-zero. But this is not true. This definitely will not happen because the symmetry. There's no difference between the set 3 and the set 1, right? So this won't happen, but this can happen. Yeah, I guess you need some more rigorous consideration. But anyway, yeah, this is our condition we have from this set of equations. Thanks for asking. Yeah, I never thought about this. I just think, okay, it's just time. Yeah. Okay. And this would give us the number equal to exponential I to pi divided by n L. Let's label the eigenvalue with L. And L equal to 0 to n minus 1. Right. And if you're really familiar with this kind of a lattice size problem, you can even assume this set is given by some superposition of n exponential I n theta, and then apply this condition and get the condition for the theta. Something like this. Because, okay, so from this guy, we also know A2 equal to lambda inverse times A1, A3 equal to lambda inverse and to minus 2 A1 and until AN, which is this guy minus n minus 1 A1. This tells us minus psi equal to, there's a prefactor A1, which will be fixed. It's just a normalization constant, right? And A1 plus lambda 1, lambda L inverse, set 3 plus lambda L to minus 2, 5, plus dot dot. So you can say the coefficients in front of the cat is given by this kind of exponential form. So for example, let's assume this guy, okay, oops. If we denote this guy to be theta, this is exactly this form at a minus sign. And this also makes sense because you can say for this state, the probability at each side are the same, right? Because they are just an exponential sum factor. And this tells us there's no difference between the set I, set 1, set 3, set 5, set 7. There's only a phase difference. And similarly, you can work out the plus what this guy is and verify the part C. And this is a part C. And you can also verify the part D. And once you have part D, you can do the part C, part E. Yeah. But I think our time is up. So I guess I can upload my the solution on the CCOE. You can take a look if you are interested in this kind of problems. Yeah, any questions?
I have a question. So previously you said that, you know, A1 plus A2 plus A3, etc. is equal to 0.
Right.
But I think that works only if, like, capital N is an even number. So for example, if you take just A1, A2, A3, for example, right? So you have e to the negative I, what is it, 2 pi over 3?
That would be this number, and this number, right?
Yeah, I think if you add them, that's not going to be 0, will it?
This is 0, just the vector addition. Cancel out with this. I'm pretty sure this is correct. So
okay, maybe, I don't know.
Yeah, so I think this is true. So for any root for this solution, it will always add up to 0, I think. Is it correct? For
I'm pretty sure if you add first two vectors, right, the length of the vector is going to be more than 1. Is it? Will it?
No. If this angle is 120 degrees, then it's not. It's the same. If I remember correctly, right? So this is okay. So basically, you're saying lambda for n equal to 3. So in this case, there are 3 values. Oh, so let's look at 1. 1 is exponential. By the way, if you have no question, you're free to go. And L equal to 0, 1, 2, right? And now we want to say number 1 plus number 2, number 3 is 0 or not. This is your question, right? And okay, so that's easy to do. Yeah, let's use a plus or let's use a minus. Okay, whatever. Doesn't matter. So this guy is 0, 1, 2. This guy is L equals 0 is 1 plus this guy is exponential is plus 1. This plus yeah, I'm pretty sure this is 0. You can show this as cosine 2 pi 3 I sine plus cosine I sine. So this is draw the diagram, right? This is minus 1/2. This is plus the length of this edge, which is square root of 3, 2. This is this angle, right? Yeah. It's also minus half. This is minus 3. So
yeah, you're right. I checked on the calculator.
Yeah. Yeah, you will always add up to 0.
Okay, that makes sense. Thank you for checking it.
Yeah,
because it's not super obvious. I can tell that for even, you know, they would kind of just like cancel by pair. But
right,
yeah,
right.
okay,
Cool.
that makes.
Thank you.
Thank you.